Hello everyone, welcome back. We started with the reaction mechanism. So in the first video we covered the basic part of your reaction mechanism, right? And in the second video we started with the nucleophilic substitutions that were occurring on the saturated carbon atoms, right? Saturated carbon atom means the one that is your sp3 hybridized, and in that also we have started with the SN2 reactions, right? So in the SN2 reactions, we have covered the approach that was taking place. That was the basic mechanism of it. We have seen its MOT approach. We have seen rate of reaction, energy profile diagram that we have seen in the last class, and we started with the factors that are affecting the rate of your SN2 reactions, right? And in the factors, we have covered two of the factors in the last class. That was about the substrate, in that we discussed how the steric hindrance of your substrate was affecting the rate of the reaction, right? And second factor that we discussed for the substrate was its electronic factor, that is when an electron withdrawing group is present in adjacent to your leaving group, the adjacent to the carbon that is containing your leaving group. So in that case, if the electron withdrawing group will be stabilizing your transition state, and the rate for your SN2 will be increased. That factors we have seen in the last class. Then we moved upon to this next factor, that was dependence upon the nucleophile. In that we have seen about the anionic nucleophiles and the neutral nucleophiles that we have seen. And then we further move to the when both the nucleophiles were anionic. In that also we have seen the factors that were affecting mainly the polarizability, electronegativity, and your bond strength. All these factors we have discussed in the last class, right? And along with that we did some of the questions also related to the dependency on these two factors. So now we are moving on to the next factor that is going to affect your rate of for your SN2 reaction, which is your solvent. So that we are gonna start today. Okay, so in the solvents, as we know that the solvent exists in the two forms. That means we can have either the polar solvents. Polar means the one in which the example, through the example we can consider water or the ammonia we can have. So in this, the atoms that are present in this particular molecule, they have the electronegativity difference, right? That are known as your polar solvents. And the other ones we have is our non-polar solvents. Non-polar solvents examples are your benzene, which is your C6H6, or your toluene is there, right? So all both of these, they are non-polar. Why they are non-polar? Because in this, the substituents that are present, there is not much electronegativity difference between them. See, in benzene we have carbon and the hydrogen atoms are just present. Electronegativity of carbon is approximately 2.5 and hydrogen is 2.1. So approximately just 0.4 value of the electronegativity difference is there. So that is not much electronegativity difference. So that is why they are called as your non-polar solvents. Okay, so furtherly, the polar solvents, they will be further categorized as your polar protic solvents, and your polar aprotic solvents, right? So in the polar protic solvents, we have is the hydrogen bonding is present, intermolecular hydrogen bonding is present, and in the polar aprotic, no such hydrogen bonding has been seen. Examples for a polar aprotic are your DMSO and your DMF is there, and for the polar protic are your water and ammonia only. Okay, so this is the further categorization of your polar solvents. So all of these solvents that is about the polar, in that as subcategorized as polar protic and polar aprotic as well as solvents. So all of these three we are gonna see one by one, that which among them we consider about the non-polar solvents. So what was happening in our SN2 reactions? So this was, suppose, your carbon center, this X was the living group, and we have the other substituents, suppose these are your hydrogens, right? So here nucleophile was coming and was denoting its electron in the sigma star of your carbon and the leaving groups, and the transition state was being formed like this X group, it is now breaking, and there is a formation of the bond between the carbon and your nucleophile. Rest bonds are remaining the same. So this is our transition state. So in the transition state, we are seeing there is gonna be the charges that will be present. So since X negative, that is going to have the partial negative charge, and the nucleophile also is your charged species, so delta negative charges present upon this. So that means the transition state that we are having in this case is our ionic, right? That means some charge presence is there. So suppose if the charged species are present, so according to the like dissolve like rule, we already know this, that polar species are stable in the polar only and non-polar species are stable in our non-polar solvents, right? And here the transition state is ionic, which means some presence of the charges there, which indicate that it is kind of your polar species, right? Because in the polar species only the development of the charge is seen. So since now we are taking the solvents to be our non-polar, so will your transition state be stabilized in that case? So answer to that is no, right? So because the ultimate motive behind the fast rate for an SN2 reaction is the stability of this transition state only, right? So since there is development of the charge and that charge stability, it cannot be attained in our non-polar solvents, right? So that means in the non-polar solvents, in your non-polar solvents, your transition state will not be stabilized. Okay, so that means these type of the solvents we generally they are not preferred. So if we have to see the energy profile diagram for this also, that we can see. So suppose this is initially the reactants and this is the activation energy that is required to get it into the product formation, right? So now what is happening in your non-polar solvents, this is the initial activation energy that is in your general normal reaction you are considering. Now if you take the non-polar solvents, now in that case what is going to happen, in fact the activation energy will be increasing in that case. That is your ea dash. Suppose this is ea dash, so ea dash is more than that of your ea. So ea dash is in your non-polar solvent, so that means rate of reaction will be lesser in the case when there is non-polar solvents. So that means the non-polar solvents we cannot refer if for the